Now we are moving on to our first case study in this course. And in this case study, we will consider linear models. This is mostly because linear models are so widely used in practice. You will see linear modeling in almost all areas of engineering and data analysis. So we wanted to cover Bayesian treatment of linear models really well as the first case study in this course. So what we will be working with is the classical definition of multivariate linear model. Our observations y will be distributed normally around what is predicted from a linear equation here. So x is a matrix of other variables, of our explanatory variables that explain observations in y. Betas would be our unknown parameters, and epsilons will be errors. We consider that all the errors for y1, y2, yn are equally independently distributed normally with the same variance. So unknowns here are our values of beta and our sigma square. We will treat them as random variables in Bayesian context, assign priors to them, and perform inference over these variables. So the likelihood in this case is going to be normal about the predicted value of y, so x multiplied by beta, with variance sigma square multiplied by identity matrix. Quite an easy thing to implement. Next thing is we will consider the conjugate prior for a normal model. So we will say that the conjugate prior is normal for parameters beta with some mean mu and some variance-covariance matrix sigma square capital M. So capital M can be chosen to be anything in our prior. It is just a prior parameter, and it is fixed because it is a prior parameter. Our prior for sigma square will be inverse gamma with some values alpha and beta as the prior hyperparameters. In your lecture notes, it is demonstrated that given this prior, the conjugate update will also be normal for beta, and sigma square is going to be inverse gamma distributed a posteriori with the following parameters. Quite an easy thing to compute using linear algebra in R. So let's see how this works on practical example, and also we will need marginal posterior distributions and we will need marginal likelihoods sometimes. All of these are derived in your lecture notes. The practical example is the Boston-Hausen dataset in an R package called ML Bench. So in this dataset, there are 14 variables taken from the census in 1970. One of those variables is the average house price, and the other variables describe other properties of houses around Boston, in different districts of Boston. The variables that will be considered will be like the number of rooms in the house, the age, which is the proportion of houses built before 1940 and after 1940, and so on. There are 13 explanatory variables. Let's try to establish a linear model over these and estimate the parameters of this linear model using Bayesian approach. So first I will load that package in R. You may need to install it if you don't have it installed with R by default. Then I load the dataset called Boston-Hausen, and this is that dataset. My values y will be the median value of the property in particular district, and there are over 500 different districts observed. X would be all the other variables in that dataset. And we will quickly reshape that X to be a matrix, where rows would be different districts in the census, and columns will be different variables in that dataset. N would be the number of rows in X, and K will be the number of variables, the number of columns in X. We will define our prior for this case for performing a conjugate update. So mean for betas will be 0, the variance will be diagonal sigma square, so just independent betas with standard normal distribution a priori. And parameters for sigma square will be 2 and 1 for some inverse gamma distribution. Now, from our conjugate update, we can find the values of m star, a star, b star a posteriori. So, this is solving of those equations for the conjugate update of prior parameters. Having this, we can now produce marginal posterior distributions of different betas, of sigma square, and so on. In your lecture notes, you will find that the marginal posterior distribution for betas, if you integrate all the other betas and sigma square out, is going to be multivariate students t distribution with new degrees of freedom, mean m, and variance covariance matrix sigma. And these are the values of nu and sigma from our conjugate update parameters. So we can substitute it all into R and plot corresponding plots for the marginal posterior distributions of different betas. So first, I'll compute nu for this students t distribution. I compute sigma. In package MVT norm, I have a function for multivariate t distribution, this one. So I will draw 10,000 samples with corresponding values of multivariate t distribution parameters. Then I can use kernel density estimation to find marginal posteriors of separate betas and also combinations of betas, say beta this one versus beta that one. All nice and dandy, except that in practice it will find a posterior that uses all the variables to explain y. And that is not particularly the most important case when introducing a linear model, using all the available information to make predictions. Sometimes we want to judge which variables are more important and which variables are less important. There are several ways of doing that, and in Bayesian approach, we will introduce a regularizing priors for model parameters. What we want to do is to say that we will prefer majority of betas to be zeros. So if you can explain your y without using a particular x, you better assign 0 as the beta parameter to that model. In that case, the variable in x will have no influence for the corresponding y. And in that case, as we squeeze majority of betas towards 0, we will use only those which are absolutely necessary to observe what happens to y. And there are several ways of doing that. So first of all, we will reshape our model a little bit to introduce an explicit intercept parameter beta 0, just because we want to avoid having to add that column of 1s to x. So we'll just mention that beta 0 will be our intercept independent of the other betas in our linear model. Now, if we assign this prior to the betas, what will happen? Then this is called the spike and slab prior. It has a spike around 0, which is a discrete density that beta is exactly 0 and has probability certain that you assign a priori. Say, I want half of the betas to be exactly 0. So with probability 50%, the value a priori is that point density of 0. And with other 50%, my beta will be somewhere within this wide uniform distribution. Any value there. But what happens here is we are directly saying that we want certain proportion of our betas to be exactly 0 unless absolutely necessary to explain why. The difficulty is that if we were to use this prior for beta, the sampler will struggle a lot to converge to stationary distribution. Normal metropolis will probably never work, and you will need to tweak your proposals in quite difficult ways to achieve convergence for this example. That's why in practice we will use a separate method called Bayesian lasso. And that method uses a simpler prior, which is called the Laplace prior. It is basically exponential prior for positive and negative values of beta. It tries to squeeze values of beta, to force values of beta closer to zero. So it has higher density towards zero. And then as we diverge from zero, the density becomes smaller and smaller a priori. So on the good side, this indeed squeezes majority of betas towards zero. On the negative side, it doesn't squeeze them necessarily to exactly zero. It may be a very small value, and at that point you will need to guess, is it that the variable is not required, that's why it has almost no influence, or whether the impact of that variable is so small that only a small value of beta is required to explain variation in y. That's the disadvantage for Bayesian lasso. On the positive side again, sampling becomes very easy. Just straightforward metropolis will work with Bayesian lasso. So here is how we rewrite that model to work with Bayesian lasso. In fact, we are just introducing Laplace friars over values of beta over here. For convenience, we decompose it as beta is normally distributed with some parameter sigma square and then matrix of taux, and that is a diagonal matrix of taux. And all of those taux would be exponentially distributed according to some parameter lambda square, which is the strength of that squeezing to zero, which is in a way again gamma distributed. This is something called hierarchical model, something we will consider in detail next week. But basically we are building several levels of priors to define a beta prior for beta. Anyway, in this case, effectively what it does is it introduces Laplace priors over values of beta. We are introducing improper prior for beta 0, so beta 0 can be actually any value from minus infinity to plus infinity with the same probability. So it is improper uniform distribution there. We still keep our inverse gamma prior for sigma square, just like in the case with the conjugate update. And let's run a metropolis sampler to evaluate the posterior for betas in this case. Obviously, this is not a conjugate prior, we can't perform conjugate update, so metropolis is the only way to get around it. And once we run it, these would be box plots for the posterior distributions of betas for the Boston housing dataset. We will find that two betas, beta 3 and beta, I believe, 7 over there, are centered around 0. So most likely those variables corresponding to beta 3 and beta 7, so x third column and x seventh column, are not necessarily required to explain the house prices. And those variables happen to be what is the proportion of non-retail business acres in town, and that means whether there is an industrial estate in the house or not. And the other one is whether the proportion of houses built before 1940, whether it is old builds or new builds. Apparently, it didn't matter in the 70s what will be the price of your house, whether it is new build or old build. Other variables seem to matter, and they play different roles in this linear model. The most largest scales, the most positive effect is obviously the number of rooms per unit, which means the larger house obviously costs more, smaller house costs less. That's why it is a big positive effect against beta 6. The big negative effect against beta 13, that is the percentage of low-income earners in the area. So obviously houses in poorer areas will cost less and houses in rich areas will cost more. And this is all kind of making sense, and we are sifting out two variables out of 13 as less important in comparison for this linear model. You can also perform inference for this example without metropolis sampler, but using a Gibbs sampler, something we will learn 2 weeks from now. And that sampler is implemented in a separate package that you can use to perform Bayesian lasso quickly. So this covers the whole case study, how to perform inference for linear models, and how to perform some simple approach to variable selection in linear models. There is no explicit homework for this week, but if you are interested, just take any example for linear modeling and try to perform Bayesian lasso on that example and see whether you can achieve good result with variable selection.